Hello everyone. So in this tutorial, I'm gonna give you a quick review on the homework assignments in Module 3. And there are several minor problems, not too many significant issues, but I still want to run through all these problems so you know what's the best way to work on that. Okay. First one. Provide the SOP and PUS and equivalent circuit, logic gate circuit of the expressions for the truth table. I actually didn't see anyone did it wrong, so everybody made it right. I don't want to waste the time on that. But second one, find the minimum sum of products. So keep in mind, you are it's asking to get all these SOPs, right? Even though this one is providing you all these max terms, but after you locate all these zeros, you still want to group the ones to get SOPs. Okay, so now let's do it from the first one. 3.21 A, B, C, 0, 1, 0, 0, 0, 1, 1, 1, 1, 0, 0, 2, these are min terms because it's a lowercase m, so it's going to be 0, 2, 5, 6. 0, 2, 5, 6. Okay, is that right? 0, 2, 5, 6. 0, 2, 5, 6. Okay, group these two, group this guy. And here's a trick. You might be wondering, should I group this single one or should I group these two? All right, so I can do both in this chapter. Doesn't matter, I won't take any points off. But the thing is, this will be the best way to do it because if you only circle this guy, there will be it's a glitch which is called a static one hazard, which is being covered in actually module 4. So you are going to learn it this week. But the thing is, you didn't know that in this module, so it doesn't matter. You can circle this one only, which is fine. All right, so let's see. What is this result? So for this row, you got these two in one group. So A naught, definitely you have this term. And which one is being toggled? I mean, toggled is being is mentioned something like that digit is being flipped, from 0 to 1 or 1 to 0. It's called toggled. Because all these logic levels are actually voltages in the circuit, right? So toggled means you turn on, turn off that bit. So you have A naught, and also you have, because B is toggle, so it's not you don't need to use it. It's got cancel. It's only C naught left, and this single one, which is A, B naught, and C. For this two, A is toggled, so canceled, and you only have B, C naught left. So that's the final result for this 3.21. The second one, R T naught, R naught S naught, R naught S. Okay, so you can imagine that one of the term, for every term here, so one of the variables is being canceled. That is because it's being toggled, right? Like what we did over here. If you think that's probably you are skipping a step in your mind, you just want to write down the full term, you can expand it. So this one is actually R S or S naught, T naught, because S or S naught will be 1, right? So this is what that looks like before it's being simplified to this version. Or R naught, S naught, T or T naught. Or R naught, S, T or T naught. And expand it. which is R as T naught or R as not T naught or R naught at R naught as not T or R naught as not T naught or R not why R not as T or R not as T naught. So until here, you can convert it back to the K map. ABC, not ABC, R as T 0, 1, 0, 0, 0, 1, 1, 1, 1, 0, 1, 1, 0, right? 1, 1, 0, you got a mean term there. 1, 1, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 1, 0, 1, 0. All right, and group these four, group these two, group these two. Do not group threes. Do not group 3 ones or 3 zeros for the max term one. Keep in mind, you are only grouping the even numbers of ones or zeros. So the final result will be this two is going to be S naught, T naught, or this 4, which is R naught, and this 2, which is S T naught. That's the final result for this one. And number 3. So the two mean terms are given, right? X, Y, Z. No, two maximums are given, which are 0 and 5. And so you know you got a 0 here and you got a 0 here. 0, 5, right? So all the other ones will be 1. And you group these two, and these two. To get rid of the static one hazard, you want to group these two neighboring ones as well. We didn't cover the static hazards in the next module, so you don't have to do that. If you do that, which is a better circuit, it's just being optimized. And that's it. So let's just use a better one, just in case. And now let's see what's the final result from this K-map. And you get X naught. Y is being toggled, so only have Z left. And this two, which is X naught, Y. And this two, which is Y, Z naught. And this two, which is X Z naught. Okay, so that's the final result without any glitches in there. You want to maybe wondering what are glitches, right? So if are working on module 4 this week, you will know what is static hazard. It's being covered over there. But no worries. Here. All right, for the next one, 3.3, find the minimum SOPs. Minimum, which means you have to, kind of simplify it. How can we simplify it? Using the K-map, right? So that's why we learn K-map, because we can simplify it without using any of these Boolean algebra theorems, right? We just do it, follow the rules, and we can get the final simplified version easily. But only limited to like up to 4 variables, right? Anything more than 4 variables will getting more and more complex. So, but in real life, we just do this kind of simplification using K-maps, for like 2 variables, 3 variables, 4 variables. But in the real life, we just totally use the synthesize tools, all these software, so they will do the computation for us, right? We don't need to do it by hand. But you need to know how to do it when you only have like 4 variables, right? So it can give you some quick results. All right, let's start working on this. So 3.31, A, B, C, D. I need a bigger table, I think. 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1, 0. And you find the sequence here in lowercase m, which means all these terms are main terms. And these should be the locations of the ones, right? So 0 is here, 2. You need to be patient about this. This is super simple, but you don't want to make any mistakes over here, right? The 1, 0, 2, 3. 3 is 1, 1. 4, 7, 8. 8 will be 1, 0, 0, 0. 14. So 14 is 1, 1, 1, 0, right? 1, 1, 0 here. And now let's group it. Group all these ones. Of course, these two, these two, these two, the single one, and these two. Okay? You can simplify it. So over here, it is B is toggle, so I only have A naught left, and C naught, D naught. These two, A is toggle, so B naught, C naught, D naught. These two, B is toggle, so A naught, C D. These two, A naught, B naught. D is toggle, so C. And the last one, which is this single one, A, B, C, D naught. Right? It's hard to simplify from there anymore, so just use it. That's 3.31, 3.32. It's a max term. CD. So the zeros are located at 1, 2, 3. 1, 1, 2, 3, 4, 9, 15. 4, 9, 15. So all the other ones are ones. So definitely you can group the zeros and getting a POS from that and finally converting to SOP, right? That's method 1. But definitely, why not directly just get a SOP from it, which will be easier. Right, so these 4 and these 2, these 2, these 2, and these 2. Okay, these are all the groups. So now let's find out. These 2 will be A is toggle, so it's B naught, C naught, D naught, or this 4, which is A and D naught, or this 2, which is B, C naught, B, and this 2, which is A naught, B, D. And the final one, the final 2, A naught, B, C. Okay, this is how to do it. You must be wondering, if you group all the zeros, how can you get a POS from it, right? So when you are working on zeros, you group zeros and you want to convert them into a POS directly. Ooh. Zero, 0, 0, 0, 0, 0. Right? These are all the zeros, like 5, 6 zeros. And let's group the zeros. 2, 2. Unfortunately, you don't have too many groups over here in the POS, which will make the inputs a lot larger. So you are going to have like 4 input OR gates. Now let's take a look. Why is 4 input A OR gates? Let's see. The first one. It is when you see a 0, you want to keep A there. It's opposite to the SOP, right? So for this term, it is actually A or B not or C or D. Keep in mind, for this one, it is A not B C D not. And this guy, which is A not or B not or C not or D not. These two, A or B, or which one is toggled? C is toggled. D not. And the last one, A or B or C not. Okay, so that's a POS. Imagine that because the problem is asking you to get a SOP finally. So you got a POS, you have to convert into SOP again. So why not just directly go from here, right? So that's 3.3, and the last one, 3.4. Remember the sum of rules, okay? Overflow only happens in these two situations, right? P plus P got an N, or N plus N, you got a P. Only these two. And you want to ask why, right? So why, then what? If you see overflow occurs, then what? Then what you want to do is adopt the carry. Because overflow happens, and the MSB carry makes sense since you don't have enough number of bits to represent the final result. You need more bits. That's why you want to adopt the final carry. The final carry, right? So that's the purpose. You just want to let the computer know the carry makes sense. You want to adopt it. You don't want to drop it. The reason we have to define this is sometimes N or P, you get a N or P, right? Doesn't whatever. But the thing is, you get a carry from this as well. Okay. So the problem is, do we want to adopt that carry or not? Definitely, the answer is not, because there's no overflow. You have enough number of bits to represent the results. Because you can imagine that you got a positive number plus a negative number, right? You already have enough bits to represent to hold these two numbers. When you are using a positive number plus a negative number, which means you are subtracting something from this positive number, so definitely you have enough number of bits to represent the results, because you get smaller numbers, smaller absolute value. Okay, so do not need that final carry, which is that's something wrong, because you are using 2's complement, right? So big why why this is wrong. The reason is 2's complement is something human beings define. It's actually not true. If I write a number over here, like 1101, what is this? Like, what the God, right? The God defines this as what? So this is 8, this is 4, this is 1, so this is 13, right? So this is from the nature. It's going to work all the time. The thing is, since we want to get negative numbers being represented in the computer, so we, like the designer or the inverter of the two's complement, they are trying to define a negative number, so they force this number to be negative a but not 8, which is wrong, totally wrong. But you are when you are adding two binary numbers together, you are doing something the nature tell you to do, right? So what you are doing, the addition, subtraction, all these operations are absolutely right. But this is not absolutely right. We define it. That's why you see this. When there's no when like you don't need the final carry, but you get a carry, right? So it's because you are using something defined by the human beings. That's why you have to design something to a digital circuit to get rid of that carry bit in this situation. All right. Keep in mind that. So let's take a look at all these problems. A 6-bit computer system. 6-bit computer system. 6-bit, right? So and 21 plus 11. So 6-bit means you have 1, 2, 3, 4, 5, 6. And for if you're looking at 21, you need a 16 first and 5, right? So 5. 16 plus 5 will be 21. And since it's a positive number, so you need a 0 in the front. What about 11? 11 will be, you need a 8 first and a 3, right? So PP. Essentially, you can get an overflow because PP, if it's n, then you get an overflow, right? 0, 0, 0, 0, 0, 1. Oops. Look at the MSB. It's a negative number. So, what you want to do? You want to adopt the front bit. Use it. Because only when you use it, you get a positive number. Because 21 plus 11 can never be a negative number. It's going to be 32. You need a 0 in the front to show a 32 to the people, to the computer. So overflow occurs. B. 6-bit minus 14 plus minus 32. So minus 32 is pretty simple for the 6-bit because you just need the 5 zeros. So it's going to be negative 32. And negative 14. Negative 14, you need a negative 16 and you need a 2, right? And you just add a 1 in the front because when you are adding a 1 to the front of the 2's complement negative number, it's not changing the value. Remember that we demonstrated that in the lecture. 0, 1, 0, 0, 1, 1, 0. And don't look at this first. Just put a carry here. And you're going to P. Overflow. Right? So you want to adopt this number because the two negative numbers adding together, it must be a negative number, but not a positive number. You need a 1 in the front. All right. C. Minus 25 plus 18. Minus 25, you mean minus 32 plus 7, right? So it's going to be 0, 0, 1, 1, 1. This is 7. This is minus 32 plus 7 will be minus 25 and plus 18. So 18, you need is a positive 18. So you need a 16. 16 is here plus 2. So that's minus 25. That's 18. Let's verify it. 16 plus 2, 18. Minus 32 plus 7 is minus 25. All right. Now let's do the addition. 1, 0, 1, 0, 1, 1, 1. So it's P and N. no overflow, right? It doesn't satisfy the condition, the concept, definition of the overflow. D, 5-bit, be careful, it's a 5-bit right now, 5-bit computer system, minus 12 plus minus 13. So what is minus 12? Minus 12, you need a minus 16 first, and you need a minus 16 plus 4, right? Is that right? Minus 16 plus 4. It's not minus 16. This is minus 16. Minus 16 plus 4. And it's a 5-bit. So that's it. It's a 5. We have 5-bit already. And plus 13. So 13, you need 8 plus 5. Definitely no overflow because you got a n plus p. There's no chance to get overflow. So this is 1 0 0 0. Right? Whatever you are getting, there's no overflow definitely. All right. Next. More paper. Now E. It's pretty interesting. I don't know why so many people have problems at E. Problem E. Let's take a look. 6-bit computer system. 1, 2, 3, 4, 5, 6, and minus 21. You need minus 32 plus 11, right? 11 will be this. 8 plus 3 will be 11. 11 plus minus 32 will be minus 21. So this is right. And minus 11 will be minus 16 plus 4. All right. Possible, right? You got n. Possibly you'll have an overflow. 1 1 1 1 1 0. Oops. Overflow. What you want to do? Adopt from bit. All right. Wait. Hold on. Let me double check this really quick. It's a 6-bit computer system. Minus 21. You need a minus 32 plus 11. So it's minus 21. And this is 16 plus 4. Oh, it's minus 16 plus 4. Wait, minus 16 plus 5, right? Sorry. This is not right. 0, 0, 0, 0, 0, boom. N. No overflow. Okay. F. 5-bit, right? So 5-bit minus 10 minus 11. So minus 10, you need 16 plus 6, which is 1, 0, 1, 1, 0. 16 plus 6 is minus 10. And for minus 11, 16 plus 5. 1, 1, 0, 1, 0. Overflow. Adopted. Okay. E. G, 5-bit computer system, minus 10 is minus 16 plus 6, right? We just did it. and -6 will be it's a 5-bit number system, so I have the same number of bits. -10 plus -6, -6 will be -8 plus 2. -8 plus 2, and put 1 in the front, so not changing the value. Right, 0, 0, 0, 0, and, right? So no overflow. H, 5-bit -8. 5-bit just make one more in the front, so that's -8, and so -11 is -16 plus 5. 1, 0, 1, 1, 1. No, 0. Overflow. The last one, I. 5-bit number system, 11 plus 9. 11 is 8 plus 3, right? It's a 5-bit number system, so you need a 0 in the front to show it's a positive number. And 9 will be this, right? 8 plus 1, 01. So PPN overflow. What you want to do? Adopt the from bit, right? So there's no carry, so the carry is 0. Just adopt it. Okay. Hopefully, if you get points taken off in this problem, try to understand it by doing more practice on that. You can just do not look at my notes and try to work on that independently by yourself. See if you can get the right answer. Okay. See you in the next video.